All right, question 15. Foresters are interested in predicting the amount of usable lumber they can harvest from various tree species. They collect data on the diameter at breast height, dBH, in inches, and the yield in board feet of a random sample of 20 ponderosa pine trees that have been harvested. Note that a board foot is defined as a piece of lumber 12 inches by 12 inches by 1 inch. So it's basically a square piece of lumber that's 1 inch thick. All right, like here's like a picture, right? It's a square board of lumber. Okay. Here's a scatter plot of the data. Okay, so I'm noticing that there seems to be a little bit of a nonlinear pattern there. It's not perfectly straight. Looks like it has an upward curve to it. Okay. Part A. Here's some computer output and a residual plot from a least squares regression on these data. Explain why a linear model may not be appropriate in this case. Okay, so it's got a high r-squared value, but the residual plot shows a clear nonlinear pattern, right? The residuals go down and then they go back up. Okay. All right, so the model is not appropriate because, one, the scatter plot doesn't really have a linear form. Scatter plot is non-linear. But even worse, the residual plot, right? That's non-linear. Right? Now, the residual plot is just a re-expression of the scatter plot that takes away the positive direction, right? So the scatter plot is curved or nonlinear, but it has a increasing trend to it, right? What the residual plot does is it removes the direction of the scatter plot so that all that's left is the form, right? And we can better see the nonlinear or the curved form. All right, so that was part A. All right, next. The foresters are considering two possible transformations of the original data. Option 1, they're going to cube the diameter values. Option 2, they're going to take the natural logarithm of the yield measurements. Right. So the diameter was the x variable, and the yield was the y variable. Okay, so after transforming the data, a least squares regression analysis is performed. Here's some computer output and a residual plot for each of the two possible regression models. Okay, so option 1, they cubed the x variable, the diameter variable. Okay, so one thing I noticed is that the r-squared value is higher than it was with the original data. And I'm noticing that the nonlinear trend is not there anymore. There isn't much of a pattern to be seen there in the residual plot. Okay. Option number 2, okay, so this is where we are using the natural log of the yield measurement. Okay, the r-squared value, 95.1, actually got worse. Ooh, okay, so that's not really good if the r-squared value got worse. Also, the residual plot still shows that there's a leftover pattern. Okay. All right. Part B. Use both models to predict the amount of usable lumber from a ponderosa pine with diameter 30 inches. Okay, so let's construct the equations first. Okay, so for option 1, we would have predicted yield equals 2.078 plus 0.004257 times 30 cubed. Actually, let's write the equation first. So this would be dBH cubed, right? Remember, that's the variable here in the first transformation. All right, So now we can replace the variable with the input value 30. So we're going to cube 30, multiply by that coefficient, and then add the 2.078. 30 cubed times 0.0042597 plus 2.078 is approximately 117. So the predicted yield using option 1 is 117 board feet of lumber. I think that was the units, board feet. Okay. Option number 2, right? So remember, this transformation was the natural log of the yield measurements. So the equation is going to be the predicted natural log of the yield equals 1.2319 plus 0.113417 times the diameter, dBH. Okay. Notice here that dBH has not been transformed. It's not been cubed or anything like that. It's just the yield, the response variable, that was transformed with a natural log. Okay. So let's replace the diameter variable with the input value 30. And we will do this calculation. 1.2319 plus 0.113417 times 30 gives a predicted natural log yield of 4.63. Okay, that seems unusually low, right? Because if we look here at the original scatter plot, 30, right, we would expect a yield somewhere in the hundreds. Okay, this model gave us a yield somewhere in the hundreds. This one is giving us a yield less than 5, right? But that's because it's a natural log. Okay, so we need to unnatural log it by using base e. So on the calculator, I'm going to do e raised to the 4.63. Okay, e raised to that, it's about 103. Okay, so the predicted yield after we unnatural log is about 103. Okay. All right, so 117 with option 1, 103 with option 2. All right, which of the predictions seems more reliable? Give appropriate evidence to support your answer. Well, I would for surely go with option 1 because of the fact that the residual plot is much more random, so there's no leftover pattern. Right, after fitting that model, and it had a much higher R squared. So I know that that model is doing a better job of predicting the variation in the yield. All right, I'm not going to write that down, but to summarize, reason number 1, right, residual plot shows no pattern. Reason number 2, this model gave the highest R squared value.